Hello again, chemistry students. This is a continuation of our notes on the factors that cause trends in the periodic table. So as I mentioned in our last video, trends are simply patterns and they are caused by different factors. So just like prices in the stock market, trends in the stock market are controlled by supply and demand, there are patterns among the elements in the periodic table that are caused by two factors, shielding and nuclear charge. In the first video, we talked about shielding. Shielding is the factor that affects the trends in elements that are in the same family. So elements that are in the same column, the ones that run up and down on the periodic table. In this video, we're going to discuss nuclear charge. Nuclear charge is the factor that affects trends in elements that are in the same period. Periods run from left to right across the periodic table, and their patterns are affected by something called nuclear charge. Now, in order to understand nuclear charge, you have to remember what particles are found in the nucleus. You have protons, which are positively charged particles, and you have neutrons, which are neutral particles, which means that all nuclei is the plural form of the word nucleus, all nuclei have a positive charge. But remember that the charge isn't just a sign. It's not just positive or negative. It's positive what? So, basically, the number that comes after the charge of a nucleus is just telling you how many protons that nucleus has. So if we take a look at the table that I have on this page, you can see that I have a number of elements. If you look on your periodic table, you'll see that sodium, magnesium, aluminum, silicon, phosphorus, sulfur, and chlorine, all of these elements are in the same row. They're in the same period. And what's happening to the number of protons as we move across the period? Sodium has 11, magnesium has 12, aluminum has 13, all the way up to chlorine, which has 17. So our number of protons, our atomic number, is increasing as we move across the period. What this means is that the nuclear charge of a sodium atom is 11 plus, and the nuclear charge of magnesium is 12 plus, and aluminum is 13 plus. So the number is telling us how many protons there are, or that's simply the atomic number, and then the plus sign just means that it's a positive charge. But like I said, all nuclei have a positive charge because they're made up of positive things and neutral things, and so the overall charge is going to be positive. So our answer for number 9 then, let's take a look at that. Now, number 9 is asking about shielding. Does shielding change as we move across a period? Well, remember that shielding involves the energy levels. So let's focus on those. So if we take a look at the number of energy levels that we have, let me make this a little bit bigger. If you take a look at the number of energy levels that we have around our sodium atom, we have 3 different rings. This inner circle around the 11, that's just a border just to show that that's the nucleus. So that doesn't count. But we have 1 ring, 2 ring, 3 rings. Same with magnesium. Same with aluminum. Let's look all the way over to the right-hand side on chlorine. Chlorine also has only 3 energy levels around it, and that should make sense to you. Because if we take a look at our table here, the period number for all of these elements is the same. They're all in period 3, which means that they're all in the same period. And remember that the period number tells you how many energy levels are found around a nucleus. They all have 3. So is shielding changing as we go across a period? The answer is no. And the answer is no because all of the atoms in the period have the same number of energy levels. So no, shielding does not change as we move across the period. All right, so there is your answer for number 9. So let's take a look at our paragraph that we have at the bottom. We're talking about shielding. It does not increase across a period. And the reason why is because all atoms in the same period have the same number of energy levels. One thing that is changing, however, and that's what I have here in this sentence, the thing that does change is the number of protons in the nucleus and the number of valence electrons. So, if we look at sodium, we have 1 valence electron in sodium, and we have 2 in magnesium, and 3 in aluminum, and 4 in silicon. So even though the number of energy levels isn't changing, the number of electrons that are in that valence shell is changing. So elements that are found in the same period don't share chemical characteristics like elements that are in the same family. Elements in families share characteristics because they have the same number of valence electrons. So the other thing that I wanted to make sure that you understood, which I mentioned before, is that as we move across a period, the number of protons, the nuclear charge, is increasing as we move across the period. So as the number of protons increases, so does the nuclear charge of the atoms. And as nuclear charge increases, we are going to start to see a number of other patterns emerge. But the thing that I really want to call to your attention is take a look at the size of the atoms. You may notice that the size of chlorine is smaller than the size of sodium. That is deliberate. That was done on purpose. And the reason why is because chlorine is a smaller atom than sodium. Chlorine has more protons than sodium does. Therefore, the nucleus has a stronger attraction for its valence electrons than sodium does. So the chlorine nucleus is going to suck in, pull in those valence electrons. It's going to make those energy levels nice and tight around the nucleus because it has 17 protons compared to sodium's 11. So sodium is still going to have like a pretty good nuclear charge, but it's not as strong as chlorine because chlorine has 6 more protons than sodium does. So sodium isn't going to draw those electrons in as tightly as chlorine is going to. So our sodium atom has a little bit of a larger diameter than our chlorine atom does. And the reason for that is because of the nuclear charge. Now, one thing that we talked about in our shielding video is that atoms that have more shielding are going to have their valence electrons further away from the nucleus. That's what we see in families. In periods, atoms that have a bigger nucleus are going to have valence electrons that are closer to the nucleus. So it's a little bit opposite in periods than it is in families. In a period, the elements that have higher numbers of protons are going to be smaller. They're going to have valence electrons that are closer to the nucleus, whereas elements that have a lesser number of protons are going to have valence electrons that are a little bit further away from the nucleus. And so when we were talking about families, we were talking about, well, which electrons are going to be lost more easily. the ones that are further away or the ones that are closer in? And the answer is the ones that are further away. And it's the same here with periods too. The elements whose electrons, whose valence electrons are further away are going to be lost easier or more easily than elements who pull their valence electrons more closely. As a rule, metals, any element to the left of the staircase, metals are going to have their valence electrons a little bit further away from their nuclei than the nonmetals are. So metals are going to lose their valence electrons more readily than nonmetals do. And the whole reason for that is because of nuclear charge. Metals in general, because they're on the left-hand side, so our metals here include sodium, magnesium, and aluminum. Our metals are on the left-hand side of the period. And so their nuclear charge is not as great as the nonmetals, which are on the right-hand side of the period. The nonmetals are going to have a higher nuclear charge, and they pull their valence electrons in closer, so those valence electrons are not easily lost. Our metals, on the other hand, have less nuclear charge, so they don't pull in their electrons very closely, and their electrons are more easily lost. And that's why our metals are going to form positively charged ions. So remember that positively charged ions form when atoms lose electrons? This is why. It's because of their nuclear charge. The nuclei of metals can't hold on to their electrons very tightly, so they just get lost, and they form positively charged ions. Nonmetals, however, tend to gain electrons. They pull electrons in towards them, and therefore they form ions that have a negative charge. It's all because of nuclear charge. Okay, so I will let you read through these last couple of paragraphs on your own, because I did just kind of paraphrase them. And now let's take a look at our check for understanding. So after reading through all of this and watching these videos, you should be able to answer these questions. So number 10 says, in your own words, explain what shielding is. So if you're studying right, you will pause the video now, write your own answer, and then come back, and then you can check it with mine. Okay, so here's what I came up with for my answer. So shielding is caused by the addition of energy levels around a nucleus, and shielding affects trends in families. The more energy levels that exist around a nucleus, the more shielding that you've got in the atom. Okay, so let's take a look then at number 11, and let's do the same thing. Go ahead and pause the video, craft your own answer, and then come back and check it against mine. And guys, mine is not the end-all be-all. As long as you say something about energy levels around a nucleus, and the more energy levels you have causes more shielding, then you gave me a good answer. Okay, let's try this now. All right, so here's my answer for number 11. Shielding affects trends in families because as you move down a family, you're increasing the number of protons and electrons. And as you increase the number of electrons, you need to have places to put those electrons. So the more electrons you've got, the more rings, the more energy levels you must have in order to accommodate those electrons. We don't have shielding in periods, because all of the elements in a period have the same number of energy levels. And so shielding does not occur. It does not affect the trends in elements that share a period. All right, and number 12. How does nuclear charge change as you move from left to right across a period? Pause it, craft your answer, and then come back. All right, so for number 12, nuclear charge is going to increase as you move from left to right across a period. And you can see this in any period on the periodic table, but if you look at period 3, Sodium has 11 protons. Magnesium, which is right next to it, has 12 protons. Across the transition metals, aluminum has 13 protons. So as the number of protons goes up, so does the nuclear charge, because remember, the nuclear charge is simply a reflection of how many protons there are in the nucleus. And so the nuclear charge also increases as you move from left to right across a period. All right, we've got one more question. Why do metals lose electrons to achieve a full valence shells, but non-metals gain electrons to achieve a full valence shell? Use the term nuclear charge in your explanation. Now remember, the metals are on the left of the periodic table and the non-metals are on the right of the periodic table. And this is going to be explained as a trend in a period. So you should not be talking about shielding here. You should be talking about nuclear charge. Try to explain this to me and then come back and then we'll see how you did. All right, welcome back. This is the last question on this page. So the question is, why do metals lose electrons to achieve a full valence shell, but nonmetals gain electrons to achieve a full valence shell? And I wanted you to use the term nuclear charge in your explanation. And so here's what I wrote. So when you look at a period, a single period, all of the metals are on the left, and all of the nonmetals are on the right. And as you move from left to right, nuclear charge goes up. So the smaller nuclei are on the left, and the larger nuclei are on the right. The elements then with the smaller nuclei in a period are the metals. And these smaller nuclei don't have the capability to pull their electrons in very close. And so the valence electrons are kind of like floating out here. They're kind of far away. And if valence electrons are far away from the nucleus, they are very easily lost. Nonmetals are on the right side of the periods, and these elements have larger nuclei. The larger nuclei are able to pull the electrons in more closely. And so those valence electrons are close to the nucleus, and they are not easily lost. So the nuclei of nonmetals actually are so strong that they have a tendency not only to pull their own electrons in very close, but they also have a tendency to attract other electrons to join their atom as well. So nonmetals are going to gain electrons in order to achieve a full valence shell and form negatively charged ions called anions. And the whole reason for that is because they have bigger nuclei, and the nuclei are strong, and they're able to pull electrons into the atom. Nonmetals, on the other hand, form cations. They lose their electrons, forming ions with positive charges in order to have a full valence shell. So when the metals lose their valence electrons, what lies beneath is a full shell, and that becomes the new valence shell. And then I have a little summary that I typed in red for you at the bottom. So hopefully this was a good video for you, and it explained nuclear charge for you and the trends in, well, not the trends, but the factor is that nuclear charge that affects trends in periods. So I will talk to you in class. I hope that you enjoyed this video. Bye-bye.